Solving triangles using trig ratios. Say we have a triangle. On this triangle, we're trying to find the tangent of angle A. So this tan A means we're looking at angle A and we're trying to find the tangent of it, or the ratio. Given that the cosine of A is 2/3. So the cosine of A is defined as that ratio as adjacent over hypotenuse. I can use this information to label my triangle and then find the tangent, that side ratio, of angle A. So cosine of A, I know the adjacent of A is 2 over the hypotenuse, which is 3. So cosine of A is the adjacent over hypotenuse, and my adjacent must be 2, and my hypotenuse must be 3. So then doing that, I know that this is a right triangle, and I can use the Pythagorean Theorem in order to solve for this side over here. So I have 2 squared plus b squared equals c squared. 2 squared plus b squared equals 3 squared. Squaring them, I have 4 plus b squared equals 9, subtracting a 4 from both sides, and I have b squared is equal to 5. Taking the square root, I only want the positive square root because I'm talking about side lengths. I have b is equal to the square root of 5. And I know, after I've got this, I can find the tangent of A. Because to find the tangent of A, I need the opposite over hypotenuse. Using the Pythagorean Theorem, I solved for my opposite side. This opposite side is now square root of 5. So to find the tangent of A, I just take the opposite, square root of 5, over the adjacent, 2. So tangent of A equals the square root of 5 over 2 for this triangle. You could also find the sine of A if you wanted to, and that would just be opposite over hypotenuse. Looking at 45, 45, 90 triangles. So we have to kind of go back to geometry and remember our side ratios. Now the 45, 45, 90 you could actually solve using the Pythagorean Theorem as long as you recognize that these angles right here help to form an isosceles triangle where this side is congruent to this side. So if we have a 45, 45, 90, here's my 90 degrees, this is 45. If this is side length L, this is also L, and then if we use the Pythagorean Theorem, we could solve to find that this was L rad 2. Now this is a ratio of sides that you learned about in geometry. So if I know A is 4, I can find C just by multiplying my side here by square root of 2. Using that, I can find the sine of 45 degrees. So the sine of 45 degrees is going to be the opposite over the hypotenuse. The opposite is going to have the same length because of the 45, 45, 90. So it will be 4 over the hypotenuse, which is 4 rad 2. So 4 over 4 rad 2, which is 1 over rad 2. Now I could rationalize that denominator, but I don't really need to do that. If you wanted to, you just multiply both the top and bottom by square root of 2, and you get rad 2 over 2. And oftentimes you'll see in trigonometry that they will have that rationalized. The cosecant of 45 is just the reciprocal of the sine. So instead of 1 over rad 2, it's rad 2 over 1, or just rad 2. Cosine of 45, and I can actually use either this 45 or this 45. I'll get the same answer. But I'll just use this 45. My adjacent, which is 4, over my hypotenuse, it's going to be the same because both the adjacent and the opposite are the same length. So I have 4 over 4 rad 2, or just 1 over rad 2. And again, the secant is the reciprocal of cosine, so I flip that over, and I just have rad 2. Tangent of 45 is opposite over adjacent. So I take opposite over adjacent, 4 over 4, which is just 1, and the cotangent is also going to be 1. Now taking a look at the 30, 60, 90 triangle, the side ratios are a little bit trickier. My short side across from the 30 degree angle is L. So any number, L can be any number. If I know what this is, I can write the other ones in terms of this L, or whatever you want to call it. So across from the 60 is going to be this same short side times radical 3. And the hypotenuse is going to be 2 times the short side. So 2L in this case. So then if I have a triangle right here and I know one of these sides, by this ratio, I can figure out what the rest of the sides are. So my short side is 5, which means my long side is going to be 5 rad 3. And this one's going to be 2 times my short side, or 10. So I can use this to help me find all of these trigonometric functions. And I can do this for both angles. Notice since they're not both 45 degrees, we're going to have some different values. So sine of 30 degrees is going to be opposite over hypotenuse. Hypotenuse is 10. 5 over 10, which is just 1/2. Cosecant of 30 degrees, just that reciprocal, so it's just 2. Cosine of 30 degrees is going to be adjacent, this A side, which is 5 rad 3, over the hypotenuse, which is 10. So 5 rad 3 over 10, and then go ahead and simplify this. 5 over 10 is just 1 over 2. So I have rad 3 over 2. Secant is just that reciprocal, 2 over rad 3. This is not rationalized. If you wanted to rationalize it, you just multiply both the top and the bottom by rad 3. So rad 3 over rad 3, which is just a 1. So tangent of 30 is going to be the opposite over the adjacent. So 5 over 5 rad 3. 5 over 5 rad 3 is just 1 over rad 3, and the cotangent is just the reciprocal. Now if we take a look at this other angle, 60 degrees, that's my angle A, we can take the sine of that as well. Sine of 60 degrees is going to be opposite, which is 5 over rad 3, over hypotenuse, which is 10. And then simplifying, rad 3 over 2. Cosecant of 60 degrees is just that reciprocal, 2 over rad 3. Cosine of 60 degrees, here we go, is the adjacent over the hypotenuse, or 5 over 10, which is 1/2. And secant of, this should say 60 degrees, 60 and 60. Cosine of 60 degrees, secant of 60 degrees is just the reciprocal of that cosine. Tangent of 60 degrees, that's going to be a little bit different because my opposite side is going to be 5 rad 3 over my adjacent side, which is going to be 5. So 5 rad 3 over 5 is just rad 3. And then the cotangent is just 1 of 60 degrees is 1 over rad 3. Now if you notice, the cosine of 60 degrees is the same as the sine of 30 degrees. And that's because if we look at 30 degrees right here, this side is opposite 30, but it's also adjacent to 60. And so that's why the sine over here and the cosine over here match up, and the hypotenuse stays the same for both. Using inverse functions. So we want to find x if we know the sine of x is equal to 0.7590. Now this is just a ratio written in decimal form, and we want to know what angle gives us this side length ratio. Well, in order to do that, this x is connected with this sine. We're taking the sine of x. So we have to take the inverse function so we can get just x by itself. Sine has an inverse function, and it's written as sine to the negative 1. Sine to the negative 1 of x is not equal to 1 over sine of x. It's just taking the inverse. So it's just like when we found the inverse of the functions and we had that f of x and f to the negative 1 of x. That doesn't mean 1 over f of x, it's just the inverse of it. So that's the same thing here. This doesn't mean 1 over sine x, it just undoes the sine function. So when we do that, we have just an x on this side, and we take this inverse sine of 0.7590, and that's found on your calculator usually as the second function over the sine key. And you also can see you have an inverse cosine and you have an inverse tangent. You don't have an inverse cosecant or secant or cotangent, and that's because you can write those numbers in terms of sine, cosine, and tangent. You just have to take the reciprocal. So here, when we do that, we get a long decimal number. Now, oftentimes they want you to round it to the nearest degree, sometimes to the nearest tenth of a degree. So if it was to the nearest degree, you would get 49 degrees. Nearest tenth of degree, 49.4 degrees. Now, if you're not getting this when you do your inverse sine, you may have your calculator set to radians. So you want to double check that you're set to degrees right now. You'll want to be set to radians later, but right now we're just talking about degrees. Now we can use information to look at this. Like this is a separate problem here, so let's just... So if we have a triangle right here, and we want to solve, sometimes it'll say solve everything about that triangle. Sometimes it'll just ask you specifics. So right here it says find angle A. So we can find angle A without even finding C. So if it wanted us to find C, we could. Depends on what they're asking here. To find C, we could just use the Pythagorean Theorem to solve for C. So doing that, we have C is equal to 15. If we want to find angle A, so take a look at angle A. we don't know what angle A is, and we only have the side lengths. So to find angle A, what we're going to have to do is use our knowledge of side length ratios and how they relate to angles. So right here, if we did a nose C, we know the opposite and we know the adjacent of this angle A. Opposite over adjacent reminds us of tangent. So the tangent of A equals 12 over 9. So we can also do this using C since we solved for C, and we could use the hypotenuse in either sine or cosine of A, but we're just going to use tangent of A here. It will work either way. So once we have that, I went ahead and reduced this. I divided them both by 3, so I just got 4/3. And you could put this in decimal form if you wanted to. So taking the inverse tangent of both sides, I just have an A here, and I take inverse tangent of 12/9, which I reduced to 4/3. And then just typing that into your calculator, you type in the 4/3 and then the inverse tangent, or you can type in the inverse tangent first depending on your calculator. You get 53.13, and that's rounded. That's actually to the nearest hundredth for my degree. Now, there are a couple ways you can do the last part, because we've got to also find angle B. Well, we know there's 180 degrees in a triangle, so, and we know 90 of it's used up right here. So we know this plus this has to be 90. So I can take 90 minus angle A, and I can go ahead and find angle B. So angle B is equal to 36.87. Now, if I didn't remember that, I could use cosine of B, or sine of B, or tangent of B. But if I used cosine of B, I would say that's equal to the adjacent over the hypotenuse, or 12 over 15. Now I could have used sine or tangent. I just chose to use cosine. And then I want to take the inverse cosine, or called the arc cosine sometimes, of both sides. And when I do that, I just have my B on this side, and then the inverse cosine of 12 over 15. And I didn't reduce it here before I took the cosine. But when I do that, I get the same answer. I get 36.87, which is the same answer I got up here. So if you recognize that, this is probably an easier way, but it will work no matter how you do it.